All right, welcome back to our exploration of climate change. And this week we're going to be looking at climate data. How do we gather and use the data that tells us what's happening in terms of climate change? So on the screen there, you see a social media post from NASA declaring that 2022 was tied for the fifth warmest year on record. We're still not quite to the end of 2023 as I'm recording this, but I'm going to guess 2023 is going to be way up there as well. And so we want to understand, well, where do we get this information, right? How do we determine whether a certain year is the warmest or one of the warmest on record? How do we get the information that's in the map that they show there that shows the temperature anomaly, how much warmer than average different parts of the Earth are? So our goals here are to explain how climate change can be measured and to understand the sources of our data about climate change. So first we want to figure out what is it that we're measuring, because climate change isn't one thing. There's not like a single number that is like the amount of climate change. There's a different types of data that we can use that will help us understand how the theory that we talked about last time, this concept of the greenhouse effect and how it changes the Earth's radiation balance, how is that actually happening in our actual world? And so I want to break it down into 3 steps of the climate change process that we can measure. And there are different kinds of data that we'll use to look at each of these 3 steps. So we can start with our radiative forcings. So if you recall from our last lesson, a radiative forcing is something that shifts the energy balance of the Earth. And our major radiative forcings that we were looking at were changes in the composition of the atmosphere that would enhance the greenhouse effect, trapping more heat on the Earth, and changes in the albedo, the basically shininess of the Earth's surface, how much of the sun's light is being reflected back out into space instead of being absorbed by the Earth. So we can measure the size of these radiative forcings. We can also measure the elements of the Earth's energy balance that is shaped by those radiative forcings. So our energy balance, we're looking at energy coming into the Earth, energy going out of the Earth, and the temperature of the Earth. Those 3 things are linked together, that our temperature rises or falls to balance out the energy coming in and energy going out, so we can measure those things. And then if our Earth's energy balance changes and our temperature changes, then that's going to have various sorts of impacts. That's going to alter various things that are happening on the Earth. And so we can measure those climate impacts to see what kind of changes are being caused by climate change. So those are things like changing sea levels, changing storm systems, etc. So let's start with our radiative forcings. So we've already talked actually a bunch about the kind of data that we can get to measure radiative forcings with respect to changes in greenhouse gases, right? We've talked about the Keeling curve and the use of ice cores to find those little bubbles of trapped atmosphere from the past, right? So those are ways of gathering data about the radiative forcings that come from changes in the composition of gases in the atmosphere. And then once we know certain amounts of gases, how many parts per million of CO2 are we at a certain point, then we can use our understanding of physics to calculate how much effect on the Earth's radiation budget that's going to have. So we've already talked a bunch about measuring the air composition and its effect on the greenhouse effect. But we haven't talked quite as much about measuring albedo. So albedo is also a very important element to climate change. It's a thing that human activity can alter quite a bit. And our best data on changes in albedo, which is really about changes in land cover, right? What is covering our land? What color is it? Therefore, how much light is it reflecting? Our data on that land cover change comes from satellites. So our longest running satellite record that allows us to get a global look at land cover comes from the Landsat satellite series that's maintained by NASA. So this is a series of satellites. They put up new ones when the old ones get worn out with improved instruments and so forth. And that Landsat data has a 30-meter resolution, which means that if you zoom in on Landsat data, each little pixel, each little block covers an area 30 meters by 30 meters of the Earth, and that data goes all the way back to 1972. And you're going to be hearing about the 70s a lot in this presentation because we get a lot of really good data from satellites, and this broad scale coverage by Earth sensing satellites really goes back to the 70s is when we really start getting this kind of data. So the image there shows you one element of this land cover change data that therefore has an impact on the Earth's albedo, which is forests. One of the big things that humans do to alter the land cover of the Earth is that we cut down a lot of forests and we encourage the growth of forests, right? We both cut down trees and plant trees. And we also do things that have kind of an indirect effect on forest cover, like we alter the burning of wildfires, right? That can have impacts on forest cover as well. So using our satellite data, we can measure how much of different kinds of land cover changes are occurring and use that to determine the changes that we're causing to the Earth's albedo. And I want to make one note here when we're looking at this particular map, because maps are such an essential part of understanding what's going on with the Earth. We've been looking at all kinds of maps all along here. And I grabbed this map. It was the first one that Google gave me. I was just looking for a map of forest deforestation, reforestation to illustrate this point. And I initially was like, yeah, this is a bad map. But then I decided I'm going to put it in here so I can tell you why it's a bad map. And the reason why it's a bad map is because this map uses something called the Mercator projection. That it's a very useful projection for a variety of different purposes. But one drawback it has is that it inflates the area of places closer to the poles as compared to areas close to the equator. So on this map, the areas of places like Northern Europe, Russia, Canada are much bigger than they should be as compared to the areas of things like South America or Africa that are closer to the equator. And so on this map, that's going to inflate the size of forested areas in polar regions. So you can see there's a lot of forests and a lot of changes. So you see like the red for deforestation going on there in a place like Canada. And it looks much bigger than the amount of forest and the amount of deforestation that's happening, say, in the Amazon in South America. But it's actually not so much bigger because the people that made this map made a poor choice about the projection to put this on. If you're showing changes in land cover, you should use a map projection that keeps the areas of things similar, even if it distorts their shapes, for example, because there's no perfect map that shows everything exactly correct in 2 dimensions when we're talking about a 3-dimensional Earth, but choosing a map projection that expands the areas of things in some parts of the Earth relative to others, not a good choice for this kind of map. So that's kind of a warning to you. If you're going and looking for data and you just, find a map on Google and you're like, oh, here's a map of this thing that I was looking for, pay attention to things like who made this map, where they got the data from, and how they're presenting the data. So something like the choice of map projection can distort our ability to understand what's going on with that data. So I deliberately chose a bad map here so that I have the opportunity to tell you that maps can be misleading and that you should always be paying attention to that and thinking about whether the map you're seeing is fairly presenting the information that it's supposed to be presenting. Okay, so moving on to talking about energy balance. One of the key elements of that energy balance is the Earth's temperature. And we as creatures that live on the surface of the Earth, we're really concerned about the surface temperature of the Earth. That's the element of climate change that makes the biggest difference for us. So, of course, we can measure the temperature, right? We just need a thermometer, look at the temperature that it gives us, and there's our temperature going on the Earth. But that's just the local temperature. Right? The temperature in just one spot you can measure with one thermometer. Some of you may even have run into the issue that, like, if you have a thermometer outside your own house, it makes a big difference if you put that thermometer someplace that's in the shade versus a place that gets a lot of direct sunlight, someplace that's sheltered for the wind versus a place that gets more direct wind. And that's just within the scale of like your front yard. But we want data on the average surface temperature for the entire Earth. That's a much bigger challenge to put together. You can't measure that with a single thermometer. What we need to do is take measurements from a huge number of different places and average them together. And our direct measurements of temperature that are adequate to get pretty reliable averages for our global temperature go back to about the 1880s. So it was at that point that we had enough weather stations around the entire world consistently recording data that we can really reliably say we can calculate what the Earth's average temperature is. And so the map there shows the weather stations that are contributing to this data for the lower 48 United States. So each little blue dot on that map represents a weather station that is recording data, and that data goes into our estimates of the surface temperature for the United States. So there's over 11,000 of these weather stations that make up what's called the Cooperative Observer Program. Now the catch is, we've got a lot of weather stations there, right? They're just thick on the ground, all blending together in some places on that map. But they're uneven in their coverage. So you can see that some areas, like Pennsylvania, has a lot of weather stations, very dense coverage of these weather stations in Pennsylvania. You look at some place like Nevada out west, you see a lot fewer weather stations, a lot more gaps in between them. So we can't just take all of these temperatures and just add them up, divide by 11,000 and get our average, because areas that have more weather stations are going to be overrepresented in the data. Pennsylvania is going to get extra weight if we just add up all of the weather stations, because we have more weather stations per area than, say, Nevada does. So in order to go from all of these observations, right, all of these weather stations that have a thermometer and record a temperature from it every day, to a number that gives us the average temperature across the whole country, and then you combine this with data from other countries and get the average temperature for the whole world, you have to do various mathematical techniques to correct for this difference, right? To give greater weight to stations that are in sparsely covered areas to make up for the having more data from other areas. We also have to factor in things about where these weather stations are located, and if there are local effects that might cause them to be warmer or colder than they otherwise would be. So, for example, weather stations in urban areas tend to measure a few degrees warmer than a weather station that's in the same area but in a more rural area. It's called the urban heat island effect. And so that can distort our data if we don't account for it mathematically. And so we have mathematical models that can adjust for that we know which stations are in urban areas, and we can adjust their temperature readings relative to the ones that we know are in rural areas. And there's a bunch more adjustments that we have to make to go from this set of 11,000 data points within the United States, plus all of the other ones internationally, to a single number for the average global temperature. And in doing that math, there are some judgment calls that you might have to make, some slightly different ways of compensating for these different error factors and so forth. And so we actually end up with 4 different global temperature series that get published. And if you look at any sort of chart of global temperatures and stuff, it should tell you which of these four it's based on. So we have one that's put out by NOAA, the National Oceanic and Atmospheric Administration in the United States. We have another one put out by NASA, a different part of the United States government. They do their own global temperature calculations. We have one put out by the Hadley Center at the University of East Anglia in the UK, and there's one by the Japanese Meteorological Agency. So these are all slightly different, but basically in agreement with each other. None of them are showing anything wildly different from the other, but they're all, just a slight bit different because they make slightly different choices about how to correct for all of the inconsistencies in the data gathering process. We can also measure temperature from satellites. So going back to the 1970s, when we start to get good coverage with Earth observing satellites, we have satellite-based measurements of global temperature. And so satellites have a couple nice advantages. One is they can give us complete global coverage and consistently image the entire Earth as they fly above us. And they can also make those measurements at different levels of the atmosphere much more easily. So if I, as an observer at a weather station on the surface, want to measure temperature, if I want to measure the temperature at the surface, right, at the bottom level of the atmosphere, that's pretty easy. I put a thermometer outside and I can see what temperature it is. If I want to try to measure temperature at different layers of the atmosphere, I'm going to go up higher than the surface, then I might have to get, say, a weather balloon, put my thermometer on the weather balloon, send the weather balloon up to a certain height and measure the temperature there. That's a more involved undertaking, whereas satellites can measure that temperature at different levels of the atmosphere much more easily. The downside is they tend to have less detailed resolution. If you want to figure out what's going on at a very localized scale, a lot of the satellites that are measuring these temperatures don't have quite that much localized detail. And the historical record is not as long. It only goes back to the 1970s, whereas our surface temperature readings, I said, we've got pretty good coverage to get global temperature averages going back to about the 1880s, so almost 100 years longer than we have satellite data for. But if we want to go back even past the 1880s, we have ways to do that. And the farther back we go, the less reliable that data is. And so the wider our error bars are going to be, our wider range of uncertainty that we have. So we have our best guess number, right, what we think is the most likely value, but then we have a range of uncertainty to either side of it. And our range of uncertainty for directly measuring temperatures with a thermometer, pretty tiny, but if we're using other methods to estimate temperature, then we start to get wider levels of error. And so these other forms of measuring temperature that allow us to go back quite a bit before the instrumental record, before we have direct global thermometer readings, are things like, first, other historical records that are just not as systematic and don't have as good coverage as the temperature records we have starting from about the 1880s. So people were recording temperatures at various parts of the Earth well before the 1880s. It just wasn't as systematic and as global, so there's more uncertainty in trying to take those records and use them to estimate a global temperature. And even going back past that, we have other sorts of historical records. So like one of the ones that I think is pretty cool is that we have diaries kept by monks in the Middle Ages. And these monks would, write down day by day what's going on, including things like when the pond at the monastery froze and when it thawed out again in the spring. And we can use that to estimate the temperatures. Right? If it's a warm year, the pond is going to freeze later and thaw earlier than if it's a very cold year. So we can use that to estimate what the temperatures would have been at that monastery. And so, of course, we don't have medieval monasteries everywhere in the world. That's a limited bit of historical data, but it's something. It can give us some idea of changes in temperature over time. We can also look at tree rings. So when trees grow, they tend to create these annual rings, right? So they grow for part of the year and then stop, then grow for the next year and then stop. And so it creates the rings that you see inside of wood. And the thickness and color of those rings is going to be affected by the climate conditions that the tree is growing under. So it'll grow differently in a warm year versus a cold year. And so we can use those tree rings to estimate past temperatures. Coral does the same thing. Coral creates growth rings. And so if you take a piece of coral and you slice through it and you look at the size of the growth rings there, that will tell you something about how warm or cold the water was that coral was growing in at that point in history. And you can figure out when you are by just counting the rings going back. So the growth rings in coral give us some ideas about past temperatures. And then our ice cores, in addition to the little bubbles of trapped air that we use to measure composition of the atmosphere, the thickness and composition of the layers of ice in our ice cores can also tell us something about past temperatures. So all of these things that are not direct measurements of global temperature, but that allow us to estimate global temperature, we call proxies. So these are proxy records. They're not direct records of temperature. They're proxies that allow us to estimate temperature. And by putting together a whole bunch of these proxies, we get one of the most famous graphs in climate science, known as the hockey stick graph. And what I've put on the screen here is actually the sort of original classic hockey stick. So you'll see that data only goes up to 1998. We would get even more of a hockey stick shape if we added the data for the last 20 years or so onto that. But I thought it's cool to look at, the original graph that made this really big splash when it came out, that the authors of this paper put together a whole bunch of these proxies. And you'll see there the blue line is their reconstruction based on these proxies. The gray is the error bars on those reconstructions. So you'll see those error bars get wider and wider the farther back in time we go. We have less certainty about our data as we get farther back in time. Then the red line is the actual instrumental data, our direct measurements of temperature. And you'll see that there's an overlap period between the blue proxies and the red actual data, and they line up pretty well during that overlap period. So that gives us confidence that these proxies are doing a good job, that we're interpreting them correctly. And so what you see there is there's actually a slight downward trend in global temperature from the year 1000, which is as far back as this version of the hockey stick goes, from 1000 up through about 1900. So up to the beginnings of the industrial era. But then after that, our gentle downward slope suddenly takes a sharp upward turn. And like I said, if we had the last 20 years of observational data on here as well, it would continue up even more. And so that shape, the long downward thing and then the sharp turn, people thought that looked like a hockey stick, right? With the handle of the hockey stick and then the blade sticking out at an angle. And this really illustrates very well how unprecedented the warming that we've had over the course of the 20th century into the 21st century has been, as compared to the temperature levels that we've had in the past. We have this much warmer conditions and getting warmer at a really fast rate that we don't see temperatures changing in the past. So on that graph, we were looking not at temperatures, but temperature anomalies. And so I think it's important to take a moment to talk about what an anomaly is, because in your lab exercise for this week, you're going to be working with temperature anomalies. So we really want to understand what this means. So an anomaly is how far off a given piece of data is from the average for that data. So a temperature anomaly is how much warmer or colder a given temperature is as compared to a historical average. So we have an average temperature, whether that's a global average temperature or average temperature for a particular place, and then we compare the current temperature to it, and however much warmer or colder it is relative to that average, that's the temperature anomaly. So we're looking at deviation from the average rather than just the absolute value. And so to illustrate this with an example that's not about temperature, you could look at the grades for two hypothetical students in a class where they have 4 exams, each worth 100 points each. So we've got Alex, who has an average across the 4 exams of 84 points. Right? So Alex is getting a B in this class, and you can see that each exam score could be higher or lower than that. So Alex's exam 1, for example, got an 88%. And so that is 4 points higher than Alex's average for the semester. So exam 1 for Alex has an anomaly of positive 4 points higher than that average. Exam 2 has an anomaly of minus 12 because Alex did 12 points worse than their average, etc. And then we have data for another student, Skylar. You see Skylar didn't do as good in this class, an average of 62. So Skylar's exam 1 got a 62, so it's an anomaly of 0. It's exactly the same as the average, but then exam 2, 53, so that's an anomaly of negative 9. Exam 3, Skylar did a little better than average, so anomaly of positive 4. So you'll notice that Alex's exam 1 and Skylar's exam 3 both had an anomaly of 4, but Alex got an 88, Skylar got a 66. Right? So the anomaly is relative to their own average. And so in both those cases, they did 4 points better than their own average, but Alex has a much higher average. So a positive 4 anomaly for Alex is a much higher grade than a positive 4 anomaly for Skylar. If you look at their exam 2s, that was a bad exam for both of these hypothetical students. Alex had an anomaly of minus 12. Skylar had an anomaly of minus 9. So Alex's anomaly is bigger. Alex did worse compared to the average on exam 2 than Skylar did, even though Alex's exam grade is higher than Skylar's, right? Alex got a 72. Skylar only got a 53. Skylar did much worse on that exam, but because Skylar's average is so much lower, Skylar's anomaly wasn't as big as Alex's anomaly. And that's an important thing to keep in mind, that the size of the anomaly is not the same as the absolute value of the thing. Because when we look at temperature anomalies for different parts of the Earth, right? So if we're looking not at a global temperature anomaly, but temperature anomalies for specific places, we tend to find that polar areas have higher temperature anomalies, but polar areas are still overall colder than tropical areas. Right? So we see greater amount of warming happening in polar areas, even though polar areas are still colder than the tropics. So if we've got the tropics up here, polar areas here, tropics warm by a little bit, polar areas warm by a lot more, but not enough to catch up to the tropical areas. We can see this if we look at this map. So this takes the temperature anomaly for a particular month, October 2022, and shows what it is for various places in the Earth. And so if you focus in on North America, what we see is that we have generally higher temperature anomalies, right? So greater amount of warming relative to the average from past years in Canada and the northern United States. And then we actually have negative anomalies. So this particular month was actually colder than average for a lot of the southern United States. So we have negative temperature anomalies, colder than average in, say, especially like the southeast there. We have positive anomalies in Canada and some parts of the northern United States. But Canada was still colder than the southeastern United States. It's still colder in Canada than southeastern United States. It's just that on average, Canada should have been even colder than that. And there should have been even more of a gap than there was, in fact, in this particular month. All right, so temperature anomaly is how far off from the average you are for that place. Okay, so now we can move into talking about some of the consequences of climate change and how can we measure the effects that climate change is going to have beyond just making our air a little bit warmer. So one really straightforward effect of climate change is reducing the snow and ice cover on the Earth's surface. If it's warmer, we're not going to have as much snow and ice. The snow and ice that we get is going to melt faster. And that's a thing that's pretty easy to measure as well. So we have ground-based observations, right? People can go out and look and see if there's snow or ice on the ground. Those medieval monks writing down when their pond froze, right? We're doing ground-based observations of this particular aspect of climate. But we also get a lot of really good data from satellites because satellites can really easily see, is there snow or ice on the ground? Is the ocean frozen or not? So in the chart there, you see the average Arctic sea ice extent in September. So September is the point when you have the least sea ice in the Arctic. So we've had all summer to melt that ice and it's shrunk down. And then after September, it starts to grow again as we move into winter. So we look at that point where it's at its smallest each year. And you see there's a clear downward trend on this graph. So if we're looking at how many million square miles of sea ice there is in the Arctic, it has gone down pretty steadily since the 70s when we first started having this good high quality satellite data to keep track of it. And there's those two little inset maps there to kind of illustrate, so you can sort of visually see how much change there is from 1979 to 2021 as two examples of kind of, extreme coverage versus extreme shrinkage of that ice cover. And this is important because there are significant ecological and economic effects that we get if our amount of snow and ice cover change. So a lot of species are affected by the amount of snow and ice cover that we have. So you've probably seen the images of, starving polar bears floating around on a tiny little ice floe, right? Polar bears need ice to be able to walk around on and to go hunting for seals and so forth. And if they don't have that ice, they can't get to their prey. That's bad for them. It's going to have a negative impact on that species. On the other hand, if we get less snow and ice, we have less to kill off ticks. And so we've actually seen an increase in the spread of ticks and of tick-borne illnesses like Lyme disease over the last couple decades because our winters aren't freezing as hard as they used to in lots of places. So it's not keeping the tick population down. They're able to survive the winter very well and explode onto the scene when spring comes along. So some species benefit from having less snow and ice. Other species are harmed by it. And for human activities, one of the big effects of changing sea ice extent is that it's becoming possible now for ships to navigate through the Arctic. So you can see on those maps in 1979, even at its smallest extent, that sea ice connected to northern Russia there for a pretty substantial area. So you couldn't really drive a ship through there. It wasn't a practical route to ship goods between, say, Europe and Eastern Asia. Whereas 2021, you can see there's pretty much an open channel from Europe across the top of Russia down into the Pacific. And so that creates new shipping opportunities. It makes it easier to prospect for mineral resources because it's pretty hard to mine or drill when you've got a lot of sea ice there. But if it's melted and you have the land and the sea are clear of ice, easier to go looking for those things, which have both positive economic effects for whoever can get up there, claim the land, drill that oil, mine that gold, whatever, and also negative environmental effects from the use of those resources. So there's a lot of potential consequences to our way of life from changes in snow and ice cover. Snow and ice cover also provide a good example of a feedback in our climate system. And this is specifically a positive or amplifying feedback. And I don't really like the term positive feedback because when you say positive, that sounds like you're saying it's a good thing. But all a positive feedback means is it's a feedback that amplifies its own effect, that you have a change in a system that causes another change, and that change increases the first change. So it spirals on itself and gets bigger and bigger. So a positive feedback is just one that increases the original change. That may be good or bad for us depending on the nature of the change. So when you see something talked about as a positive feedback or then a negative feedback going the other direction, something that balances out or reduces the original change, those aren't positive and negative in the sense of like good or bad. They mean increasing or decreasing the original change. So this positive feedback that we have with snow and ice cover is called the ice albedo feedback. So you'll remember that ice has some of the highest albedo of any land cover that we've got on Earth. Right? Ice is very light colored, it reflects away a lot of sunlight, and so it has a cooling effect. Right, so it needs to be cold for ice to form, but then once you have ice, that ice cools things off by reflecting away a lot of sunlight. And so if you increase the temperature, as you see in the top box in this little diagram, that's going to melt sea ice. You have less ice, and we're going to replace this bright white sea ice with very dark colored water. Water in the ocean is very dark colored. It's kind of the opposite end of the albedo chart from ice. So you go from your increased temperature causes your sea ice to melt, so your albedo goes way down. Your Earth is now absorbing most of that incoming sunlight instead of reflecting it away. And when your albedo decreases, you're absorbing more of that solar energy and then radiating it back out as long wave infrared heat radiation that can be absorbed by greenhouse gases. That's going to increase the temperature. And then the increased temperature is going to melt more sea ice, which is going to reduce the albedo some more, which is going to increase the temperature some more. So it's a positive feedback loop. It keeps increasing the original temperature. And this has the potential to just keep going and going and going until we run out of sea ice to melt. Right? At some point, this particular feedback comes to an end because there's no more sea ice that we can melt. But this is a pretty serious feedback. And it's one of the reasons that polar areas have been warming faster, right? Have a higher temperature anomaly than tropical areas, because it's only in the polar areas that you have enough ice to create this ice albedo feedback. Another consequence of climate change is increases in sea level. So the first thing to keep in mind about sea level is that sea ice does not increase sea level when it melts. So when we are looking at increased sea level, a big contribution to that is more water being added to the ocean by the melting of ice. So we have ice in solid form, it melts, becomes water, goes into the ocean. More water in the ocean means higher sea level, right? That only really applies to continental ice sheets and glaciers. So ice that is sitting on the land. Because if your ice is in the ocean, if it's sea ice floating in the ocean, the ice is already displacing water and contributing to the rise in sea level. So when that ice melts, it doesn't change the sea level. It doesn't add any new water. That water was already in the ocean. It's just changing from being in the ocean in solid form to being in the ocean in liquid form. And that's the same reason why if you have a glass of water with some ice in it, if the ice melts, your glass doesn't overflow. Right, that water was already in there in ice form, and it's now just switched to water form. On the other hand, if you were to hold an ice cube in your hand above your glass, as that ice melts, it would drip down into your glass, and it could cause your glass to overflow. You're adding additional water to it because that ice was not already in the water. So the melting of ice sheets and glaciers that are on land, that are on the continents, and the two big ones here, of course, are Antarctica and Greenland. So the Greenland ice sheet, the Antarctic ice sheet are the big ones. They have lots of water to potentially contribute to the ocean and raise sea levels. But that's only part of what's causing sea level rise. Because we also have what's called thermal expansion. So as water warms, it actually swells up a little bit. It gets a little bit larger in volume as it gets warmer. And this is something that's small enough that you're not going to see it if you put a pot of water on the stove and turn the stove on. You're not going to see that water level rise. It's very small. But when you have the volume of water of the entire ocean, you warm all of that up by a degree, that creates enough thermal expansion to make a noticeable difference to global sea level. So you've got this added water from melting continental ice sheets, and then you've got thermal expansion of the water that's already in the ocean. And so if we put these things together, what you see on the chart there, the black line is satellite measurements of global sea level. So we can use satellites, they can ping a signal off the surface and tell you exactly how high the surface of the Earth is, and we can compile those measurements and we can get changes in our global sea level to a very high level of precision from our satellites. So that's the black line there. The red line shows the amount of change that's due to thermal expansion. The blue line shows the changes that are due to adding water to the ocean from melting glaciers. And you can see that adding that water is a little bit bigger than thermal expansion, but then you add those two things together, you get the purple line, and that's showing us the changes that are due to the combination of thermal expansion and added water. So those two things, the added water is a little more, but thermal expansion is still making a pretty significant contribution to our sea level rise. Now, we also have to factor in, there are things besides temperature change that can contribute to changes in sea level, particularly if you're looking at a specific place, right? You're looking at a particular bit of coastline, and is the sea level getting higher or lower over time. So in addition to thermal expansion and adding meltwater to the oceans causing sea level rise, you have things like erosion and deposition along coastlines. Right? Your apparent sea level is going to seem to go up if you get a lot of erosion removing the land there, and vice versa if you've got a lot of deposition building up more land. There's post-glacial rebound, so a lot of areas, including the eastern United States, got squashed down by the weight of the ice sheets during the ice ages. And after the ice retreated, the land is very slowly bouncing back. It's very slowly rising back up to where it was before the glaciers came along. So that post-glacial rebound can cause a seeming drop in sea level if the land itself is going up. You've also got coral growth in some areas. If you've got active coral reefs, they're growing, and they can be sort of lifting the land up. So you've got these other factors that have to be taken into account when you're looking at sea level rise at a particular place. But these satellite measurements of global sea level rise show pretty clear evidence of what we know to be one of the very straightforward effects of climate change. It's also important to keep in mind that sea level rise is something that responds slowly to temperature increase. Right? So just like if you have a lukewarm glass of water, you drop some ice in it, it's going to take a while for that ice to actually fully melt and even out the temperature within your glass. So the same thing is true for the melting of glaciers and for that thermal expansion. That changes in temperature will cause these changes, but they take time to happen. So even if we were to stabilize our Earth's temperature, if we were to stop the increase of temperature, we would probably see sea level rise continue to occur, because it's going to take a while for the system to come into equilibrium with this new higher temperature. The chart there shows projected sea level rise in a couple different scenarios for climate change. So the bluer line is a scenario of less warming. The red line is a scenario of more warming. And you may look at that chart and say, okay, they're projecting even the worst case scenario by 2100, something a little under a meter of sea level rise. Is that a big deal, right? Less than a meter of sea level rise? Well, that actually is a big deal for many very low-lying coastal places. So places like Florida or Bangladesh that are very close to sea level already, less than a meter of sea level rise can cause serious problems for everybody that lives along the coast and at very low elevations. And we have some small island nations like Kiribati or the Maldives that are only a meter or two above sea level at their highest point. So they're composed of these coral islands. The coral isn't growing way out of the water, so they're barely above sea level to begin with. And even a small amount of sea level rise like this can potentially make those islands uninhabitable by people. So sea level rise is a pretty serious thing if it happens to the degree that we are projecting that it will, and a degree that's consistent with the measurements that we've already taken. Okay, another consequence that we can get from climate change is changes to hurricanes. So a hurricane is a tropical storm with winds of at least 119 kilometers per hour. So that's the threshold that makes you go from a tropical storm to officially a hurricane. And we get hurricanes in various parts of the world. They tend to be called typhoons or cyclones in some parts of the world, but it's the same kind of storm. It's the same phenomenon that we call a hurricane when it happens in the North Atlantic. And so I'm going to keep talking about hurricanes because that's what we get for the most part here in the United States. Hurricanes are huge storms that are driven by energy that comes from the warm ocean. So as the ocean warms up, causes that water to evaporate. And as water evaporates, it picks up energy. So it sucks in energy as it evaporates. That's why sweat makes you cool off, because as the sweat water evaporates off your face or whatever, it is sucking up energy to do that, to make that phase change from liquid to gas. And it's pulling that energy out of your face and cooling you off when it does that. So as water evaporates off the ocean, it's picking up that energy. Then it's going to release that energy when it comes back into liquid form. So that water vapor that's going up into the atmosphere, the atmosphere is going to cool off and cause it to recondense into liquid water droplets, and that's going to release that energy. And that release of energy is what powers our hurricane. And so if we have warmer water, it's going to cause more evaporation. And so there's going to be more energy taken up into a storm like a hurricane. And so then the storm is going to release more energy as it blows. So that tells us we should expect worsening hurricanes as a consequence of climate change. So to determine whether our hurricanes are worsening, we need to measure the strength of those hurricanes. And there's two main ways that we see hurricanes' strength talked about. So one, probably the more common one that you're going to see on like news reports and stuff, is what's called the Saffir-Simpson hurricane wind scale. And this divides hurricanes into 5 categories based on their top wind speed. So we measure the top wind speed going on in the hurricane, and based on which bucket that falls into, we call it, category 1, 2, 3, 4, or the strongest ones are category 5. And the chart there shows the exact cutoffs of wind speed there. That's not something that you need to memorize or anything, but just know that there are 5 categories. Category 5 is the strongest hurricane. Category 1 is the weakest. And so when you're hearing the news reports about this certain storm has strengthened from a category 2 to a category 3, right? It's going up a step in this chart. It has crossed that threshold of wind speed, and the stronger the winds are, of course, the more damage that hurricane is going to be able to do. And it's really the wind that's doing most of the damage in the case of a hurricane. And that image there of the Saffir-Simpson wind scale is describing the kind of damage that those winds might do, because if I tell you the winds are 200 kilometers per hour, that might not mean much to you. You might not be able to visualize or imagine what that can do. And so this presentation of the Saffir-Simpson wind scale is giving you some kinds of effects, things that you would see if you got winds of that speed. But we should keep in mind when we look at this our discussion of vulnerability, right? How much damage those winds are going to do is going to depend in part on things like what kind of architecture we have. Right? So you see the windows of that house starting to break as you go into higher categories. Well, exactly at what wind speed those windows are going to smash out has a lot to do with what kind of windows they are, right? What they're made out of, how well they've been maintained, etc. So it's not purely the wind speed that is causing the differences in damage. It's also the vulnerability of the things that we have built to being damaged. So that's one way that we can measure strength of hurricanes, is by these categories on the Saffir-Simpson scale that's based on top wind speed. There's also what's called the power dissipation index, and that's a measurement of the total amount of energy that's being released by the hurricane. So the hurricane has been drawing up all this energy, and it's releasing it in the form of these winds. And so if we measure the energy, then we're getting our power dissipation index. So it's just another way to measure the strength of hurricanes. So here's some data about hurricanes, and this is specifically looking at hurricanes in the Atlantic. So again, the ones that are going to affect the eastern United States. And so one thing we might look at is the number of hurricanes. Right? Are we getting more hurricanes happening? A larger number of storms. And so the first thing we might focus on in that first graph is the green line, which is the total number of hurricanes that are happening. So, and if we look at that line, we see it's got kind of an upward slope going from the 1880s up to the present day. It kind of seems to be going generally upward. But then you might also notice that there's that orange line there that says total hurricanes adjusted. So why would we adjust the number of hurricanes? Well, it has to do with our ways of gathering data about hurricanes. How do we know when there's a hurricane? So for most of this period covered by this graph, the only way to know that a hurricane was happening was for it to hit somebody. So it had to make landfall in a place that had population that would, record it and report that there was a hurricane, or it had to cross the path maybe of a ship sailing across the ocean. The ship would know their position and would report that they had encountered a hurricane. And then we can later figure out, which of these people were observing the same hurricane and so forth. But a hurricane had to cross somebody's path for us to know about it and to include it in our data set. But people aren't everywhere, certainly not in the ocean. And so especially in the earlier parts of the time period covered by this graph, there may be hurricanes that went unnoticed. Hurricanes that never ran across any people and therefore never entered into our records. But starting in the 1970s, we have satellites. So satellites coming back again, changing our data as of the 1970s. With a satellite, you can watch the whole ocean. It doesn't matter if there are people there or not. You can watch from above the entire ocean. And so once we have satellites, we can be sure that we are detecting every hurricane that comes along. So we don't have to adjust those numbers after we have satellite data. But by comparing the hurricanes that we detect from satellites versus the hurricanes that actually hit anybody, we can figure out how to adjust those past hurricane records to account for the fact there were probably some hurricanes happening that never hit anybody and didn't get into our records. So there you get the orange line there. Once we put that orange line in, you can see that it looks generally kind of flat. Right? There are ups and downs going on, but there's not an upward trend anymore. Once we account for that gap in our data, once we account for the fact that that older data was missing some hurricanes. And another way to confirm that is if we look specifically at hurricanes that made landfall in the United States. Right? So there, we're looking at hurricanes just in one specific place where we know that everyone that hits the United States, somebody's gonna notice it, right? There's not areas of the United States that are so big and desolate that a hurricane could hit and nobody would take notice. And if we look at that subset, look at hurricanes that hit the United States, so we know that that issue of hurricanes going unnoticed isn't going to affect that data. It's flat. There's no upward trend. So climate change is clearly not causing an increase in the number of hurricanes that we're experiencing. But number of hurricanes is just one way that our hurricanes can change. What if the hurricanes that we do get, again, same number of hurricanes, but they're getting stronger? And we're getting stronger hurricanes. So that's illustrated by the second graph there. And so that is the total power dissipation index shown on the solid orange line for all the hurricanes occurring in a year. So we're taking our amount of energy that's coming through in our hurricanes. And there we see an upward trend. We see more energy coming from our hurricanes. So our hurricanes are getting stronger even though we don't have more total storms. The storms that we do get are stronger storms, greater on the power dissipation index, greater on the Saffir-Simpson scale. So we're getting, more Category 5 hurricanes than we had in the past, more Category 4 hurricanes, etc. All of our hurricanes are being shifted upward in their strength. And so that's data that's confirming something that we would expect from climate change, that as our sea surface gets warmer, there's more energy going into the hurricanes, and the hurricanes are going to get stronger. So I want to close out this lesson by talking about the question of attribution. So attribution means placing the blame for an event, essentially. It's the process of determining the degree to which a particular cause, such as climate change, is responsible for a particular effect, some sort of weather phenomenon like a heat wave or a hurricane or a drought or whatever other weather event that we're looking at, right? So how much did a particular cause, such as climate change, contribute to this extreme event happening? And over the last 10-ish years, we've gotten really good at doing these attribution studies after every major event that happens, every big hurricane, every big drought, etc., people are going to jump in and do some of these attribution studies to determine how much of this can be attributed to climate change. And the chart there shows numbers compiled from a whole bunch of these attribution studies, so studies covering 190 different extreme weather events, and you can see for each type of weather event how many of them were attributed to climate change. So that is the conclusion of the study, was that this event was more severe than it otherwise would have been, or more likely to occur than it otherwise would have been because of climate change. Right? Climate change made this event worse or more likely to happen. That's in the red. Purple means climate change is making it less severe or less likely to occur. Blue means they couldn't detect any influence of human-caused climate change. And the gray means there was insufficient or inconclusive data. They couldn't be sure. And so you see quite a lot of attribution to climate change, that we can say that lots of our heat waves are being made more severe or more likely to occur by climate change. Lots of our droughts are being more severe or more likely to occur due to climate change. You can see down there the storms bar is kind of split, right? We've got a substantial number of them being made more severe, more likely to occur by climate change, a substantial sort of similar number of them that they determined there wasn't a human influence, and then a good chunk where they didn't have sufficient data to say one way or the other. And then, of course, cold and ice, you would expect a big purple bar there that climate change made those less likely to occur or less severe when they did. So we can do these attribution studies to try to pin blame for specific events. But I think in general, it's better if you don't have a really good attribution study for a particular event, a particular hurricane, a particular drought, whatever. It's usually better, it's usually safer and more accurate to say climate change is making events like this more common rather than climate change caused this event. So if there's a big hurricane, it's better to say climate change is making hurricanes of this magnitude more common rather than saying, climate change is the cause of this hurricane. Okay, so that should give you what you need to be able to get started on your lab exercise for this week, where you're going to be using Excel to visualize some climate data and do some basic analysis of that data.